everyone, and thank you very much for joining this presentation. My name is Viktor Zaverkin, and I'm from NEC Laboratories Europe in Heidelberg. Today, we are going to talk about uniformly accurate interatomic potentials, and more precisely, we will talk about how to learn them from scratch, meaning how to learn them without any prior knowledge about the atomic system of interest. Before I will start talking about the details of the methods we have proposed to learn uniformly accurate interatomic potentials, I would like to explain you why machine learning plays an important role for modeling molecular and material properties. And this is quite straightforward because we want to transfer their quantum mechanical accuracy to larger time and length scales to get molecular and material properties at the desired level of accuracy, which is typically not provided if we use classical force fields because they model the interactions between atoms using this simple spring model. Modeling molecular and material properties at the desired level of accuracy, as for example, density functional theory, often means running large-scale atomistic simulations, as for example, molecular dynamics simulations. And this can be quite computationally expensive because this often means evaluating energies and forces for a large number of atomic configurations. Machine learning helps us to reduce this computational cost by allowing to learn the surrogates from explorative simulations run for shorter time and smaller systems. And here, explorative simulation means that this is a simulation run to explore the phase space of their atomic system we are investigating. We can improve the computational efficiency of the data generation and surrogate training by using active learning, which iteratively improves our surrogate here. What do we propose in our work is to replace the DFT-based explorative simulations by those run by using the intermediate surrogates, but more on that later after I explain to you how do we construct machine-learned interatomic potentials and why data plays an important role for these. So machine-learned interatomic potentials aim to map an atomic system, shown here on the right-hand side, to its energy. And they do this by using highly parameterized functions with the parameters theta here learned from training data, such as energies, atomic forces, stresses, and so on, evaluated at their desired level of accuracy. We also assume the locality of interatomic interactions to allow for scalable models, meaning for models which can be trained on smaller systems and then transferred to larger ones. And locality of interatomic interactions means that, for example, this carbon atom interacts only with the atoms within the predefined cutoff radius and given here by the R max. Practically, it means that we decompose our total energy by the sum of its local contributions, atomic energies, which depend on the local environment here. It appears that using their local environments as they are is not a good idea because they do not reflect their invariances or equivariances of properties we want to predict. And therefore, they have to be transformed into a suitable input for machine learning techniques. And by the way, in our work, we do imply neural networks. I'm not going to talk about this transformation of local environments to a suitable coordinate system, and will mainly focus on training data generation in this talk, as it appears to be a key challenge. We see that it's impossible to train a good interatomic potential without the data, and we have seen in the previous slide that it's quite computationally demanding task. I would like to add at this point that generating the training data requires also exploring their complex compositional and configurational spaces, meaning the spaces spanned by the atomic types and atomic coordinates. We tackle the data generation challenge by using uncertainty-driven active learning. And here on the left-hand side, I show you the high-level structure of our active learning approach. There we first randomly perturb the initial structure to get the initial training data set, and then iteratively learn intermediate potentials until we get a final model. But what does happen during in a single iteration? So given the current training data set, we train our surrogate model, intermediate surrogate model, including uncertainty calibration. And on the next slide, I will explain why we need uncertainty calibration. And then we use these intermediate potentials to run explorative simulations. More precisely, we run multiple of them in parallel. And then we use the batch selection strategy to select a subset of informative and diverse structures from unlabeled trajectories, which we provide then to, for example, our DFT solver to compute the reference, energy, and force labels. What does happen during the exploration simulation? And here, first of all, I should say that exploration simulation is just a normal atomistic simulation. There we first of all update our forces and stresses and then use them to update the positions. However, we augment this standard atomistic simulation by evaluating the uncertainty of our model, and this mainly to be able to say after we updated the positions whether the force prediction will be accurate or not. If it's accurate, we continue with the atomistic simulation, and if not, we essentially terminate it and then provide unlabeled trajectory to the selection and labeling step. We also augment our atomistic simulation by uncertainty bias, and this is because we want to enhance the exploration of rare events and extrapolative configurations. And rare events here means that we want to accelerate the exploration of the events which happen infrequently during the given simulation time. And extrapolative configuration means that we want to accelerate here the exploration of the configurations on which our model would make a wrong force prediction. Of course, like here, we have seen that uncertainty quantification plays an important role. And therefore, I decided also to provide you a few details on how do we compute the uncertainties. And first of all, to compare it to the literature approaches, I want to mention that typically people use an ensemble of models to estimate the uncertainty. Means that they train several models and then estimate the variance of their predictions to get the uncertainty. What do we suggest is to use gradient features here, which can be interpreted as a linear response of our model to a small perturbation in the parameters. Also, we can obtain them by, for example, expanding our energy expression into its Taylor series around the optimal parameters and get in these Bayesian linear regression here. What I also want to mention here that, of course, due to the locality approximation, our gradient features can be decomposed into the local contributions into atomic gradient features here. And this allows us to compute uncertainties for global and local properties such as total energy and atomic forces. And for these, we use typically the square distances between the gradient features or directly compute the posterior uncertainty. An example of the posterior uncertainty defined for a local property is shown here. So as a final remark, I wanted to mention that we use sketching technique to make our approach essentially computationally efficient, and this is because gradient features are highly dimensional, and we use sketching technique to reduce the dimensionality of our gradient features. Now I would like to say a few words on why we want to calibrate our uncertainties, and to understand these, let's imagine we want to run dynamic simulations to generate our training data, and this requires essentially to set a reasonable threshold value for our uncertainty, which reflects their onset of their extrapolative regions. And if it does not correlate well with their actual error, or it doesn't represent well the actual error, we will explore very fast highly distorted and unphysical configurations, which again leads to bad force and energy predictions, and that means it leads also to bad final models. What does error underestimation actually means? And I show it in this graph here. And essentially, it is these points here which lie above the red line. That means their estimated uncertainty is lower than the actual error. And to tackle this problem, we propose to use inductive conformal prediction, which essentially takes the largest errors here and then adjusts the uncertainty values such that they are moved onto this red line or below it. So we use for these the ratio between their actual error and the respective uncertainty. So now a few words about the data set we use to generate this graph. And we use here the data generated in this publication here for the metal organic framework. And their upper panel here represents essentially their their models performing on the data created by random perturbation of the initial configuration, essentially mimicking what will happen in our first iteration, our active learning algorithm. The lower panel represents the performance of our model trained on their data generated during the metadynamic simulations. And before I will move on and we'll talk about uncertainty bias, I would like to say a few words about the comparison between our ensemble-free uncertainties and the ensemble-based technique. And we see from these graphs that our ensemble-free uncertainties perform comparably well to the ensemble-based technique, but they are more computationally efficient by about a factor of the number of models used to build the ensemble. Now a few words about how do we bias our molecular dynamic simulations or atomistic simulations using the uncertainty. And here the solid black line represents the intermediate potential or the potential energy surface predicted by the intermediate potential model. And we subtract their uncertainty here to essentially force our system to move on this dashed line here, facilitating the exploration of these high uncertainty regions, and at the same time, exploration of the second basin, because we also reduce the barrier here. What we do in addition to these is that we use all previous gradients. It means their forces predicted by our model and their uncertainty gradients to rescale the biasing strength here or here and gradually increase their uncertainty driving such that we explore the both extrapolative regions and rare events also in the later iterations and span the largest possible phase space we can. We augment our uncertainty bias by automatic differentiation to go beyond the atomic forces here. And for example, introduce bias stress tensor or the concept of the bias stress, which can be used, for example, during molecular dynamic simulations and constant pressure to essentially explore the larger portion of the phase space of interest. Now a few words about metadynamics and how it compares to our approach. So essentially metadynamics tries to fill this basin by the Gaussian functions and do it gradually such that we essentially do the diffuse motion in between, which is quite slow, and therefore it spans essentially smaller phase space than our uncertainty bias simulations. Now, I mentioned that we run multiple parallel atomistic simulations to explore the relevant phase space, and this can lead to an issue because in the later, like in their first iterations, we do uncertainty biasing and we probably generate highly diverse final configuration or highly diverse uncertain configurations. But whenever our model learns, there is a chance that we generate highly correlated uncertain configurations. And this can lead to the deteriorated performance of our model because we would select, if we would just use the uncertainty to select the data, we would select the highly clustered data as shown here. And I should mention at this point, of course, that our goal is to improve the computational efficiency of the approaches. It means we want to select multiple structures without retraining our model. And we suggest to do it in a greedy fashion by enforcing enforcing the diversity of the selected structures. As for example, shown here, there we essentially select the data such that they span their explored space uniformly. We can also enforce the representativeness on the selected data, meaning that we can focus more on the denser regions, but it appears not to be an appropriate strategy for the dynamic setting used in this work. Now we can talk a bit about the results we have obtained by using our active learning algorithm. And I would start by introducing the results obtained for Alanine dipeptide, a model which is used quite often for benchmarking enhanced sampling methods. And in our framework, we initialized active learning by using 8 randomly perturbed configurations and use their bias stress to drive our dynamics to unexplored regions. I should also mention that we reduce the biasing strength of hydrogen atoms to 0 because we want to reduce, these high frequency oscillations, and to actually make their exploration of their slow modes more efficient. So if you look at these panels here, we see that compared to unbiased molecular dynamics simulation at 300 Kelvin, we explored their space of these two dihedral angles, these two slow modes, more efficiently if we bias their atomistic simulation, their molecular dynamics simulation, by our uncertainty bias. And their coverage here is improved by a factor of 1.6. And this, of course, correlates to improved energy and force RMSEs by factors of 15 or 2. So whenever we increase the temperature, we will improve also, of course, our coverages, but we do not reach the performance of our uncertainty bias molecular dynamics. And only by increasing the temperature to 1200 Kelvin, we can do so. But of course, we deteriorate the performance of our algorithms by increasing their temperature to very high values in the initial iterations, because there our intermediate potentials do not know what to do with their strong distortions, which these high temperatures actually do. And another disadvantage of the high temperatures is essentially that whenever we use models which allow bond breaking and bond formation, they can degrade, high temperature can degrade the structure, meaning it can destroy it. As a second example, I would like to introduce the results obtained for a metal organic framework, which features two stable phases, the closed pore and the large pore ones, and their transition between them is triggered by increasing temperature and pressure. So we initialize our active learning algorithm by using 32 randomly perturbed configurations and use bias stress to drive the dynamics toward unexplored regions. So for these high temperature experiments, I would like to compare the results obtained by our uncertainty biasing to the metadynamics. And first of all, we see that both methods explore both stable phases of the metal organic framework, but our uncertainty biasing leads to more efficient exploration of the smaller volumes, which leads to a much better performance of our models in this region, and also the uniform accuracy across the whole volume space. And this led us to argue that uncertainty biasing essentially leads to uniform error reduction, while classical enhanced sampling methods such as metadynamics merely want to sample their relevant phase space uniformly. Now we want to reduce their temperature to actually reduce the probability of the transition between the both states, and train our initial model on more data generated around the closed pore state, to reduce the possibility to actually explore the large pore state, because whenever we have not learned how steep the energy increase there, our model can simply underestimate it and then just explore the large pore state. And this everything is done to essentially see whether our bias stress can also do enhanced sampling. And the answer is yes, because we see that our model has explored both. Our uncertainty biasing has explored both large pore and closed pore stable phases, but again, was driving the dynamics towards smaller volumes, because their other models essentially do not perform well in this region of the volume space. Now I would like to say a few words about the extent to which uncertainty bias leads to enhanced exploration of rare events and uncertainty and uncertain regions, these extrapolative regions. And for this, we performed autocorrelation analysis. There we computed the autocorrelation function and autocorrelation times. And first, I would like to refer to this upper panel here. There we study their autocorrelation function in the position space, and the faster their respective autocorrelation function decays, the faster our molecular dynamics explores the respective space. And here on the right-hand side, we show their respective results for the uncertainty autocorrelation functions. Yes, what we do learn from these graphs here, and while their top panel shows us the results for alanine dipeptide, and the bottom panel shows us the results for the metal organic frameworks, that our uncertainty bias, meaning there's all of these bias forces and bias stresses, leads to the exploration of both spaces, their position and uncertainty spaces, faster by a factor of up to 6 compared to unbiased simulations, shown here by the blue line, by the blue color. Also, we observed that our uncertainty bias simulations explore the space comparably fast to the harsh conditions, meaning high temperatures and high pressures, while not imposing any prior knowledge. So like prior knowledge in this case means knowing the temperatures at which all relevant transitions can happen, and we can explore these transitions without imposing this knowledge. With that, I would like to summarize my presentation, and what we have observed is that our uncertainty-driven active learning, which uses uncertainty biasing during the exploration phase, helps to construct training data sets which are as small as possible, but cover as large as possible relevant phase space, improving their computational efficiency of data generation, and as everything is without any prior knowledge on their transition temperatures and transition pressures. I also would like to highlight that we have shown that using our approach, you will obtain uniformly accurate interatomic potentials. And this again, because we do explore simultaneously the rare events and their extrapolative configurations. I also have highlighted few methodological advances, as for example, ensemble-free uncertainties derived from gradient features, or calibrating our uncertainties with conformal predictions. But I also highlighted the necessity of selecting diverse batches if you run multiple parallel atomistic simulations. With that, I'm done with my presentation and would like to thank you for your attention. Thank you very much.
Orchestrating a Brighter World, NEC.